change bits to 1, you use so here's OR, here's AND, here's XOR. Which one looks like it might be useful for changing a bit to 1? OR, right? So if you want to change bits to 1, you use OR. If you want to change bits to 0, you use AND. If you want to change the value of a bit, you want to flip it, you would use if you'd like to flip a bit, which bitwise operator do you use? Use XOR, right? This kind of chart here gives you an idea of how you can utilize them, right? If we OR something with 0, it stays the same. If we OR something with 1, it becomes 1, because true OR something is true. If we AND something with 0, it's going to become 0. If we AND something with 1, it's going to become itself, right? It won't change. True AND something is dependent on the other thing, but false AND something is always going to be false. If you XOR something with 0, it's going to be still whatever it is, because false XOR false is false, and true XOR false is true. If you do true but if you XOR something with true, it'll be the opposite, because false XOR true is true, and true XOR true is false. So you can flip bits with XOR, right? Now, lots of times you want to be able to work with the ith bit, right? Change the ith bit, read the ith bit, do something with bit I, right, where I is some variable amount. The way that you can get this is by combining the bit shift operators with whatever it is that you want to change it to, or change it to, right? If we think about the bit pattern for 1, right, what's the bit pattern for 1? Right, the bit pattern for 1 is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, right? So if I wanted to check bit 0, 1 is fine because it's going to be at position 0. But if I wanted to check bit 2, right, I'd have to move that 1 over into the second spot, right, into index 1. If I wanted to check the bit at index 2, I'd have to, again, move it over to get to that spot. So notice we have this original bit pattern 1, and it moved over which direction, left or right? Left. This one is, again, moving left. Right? So if you want to get a 1 at position I, what can you write to make a 1 appear at position I, where you may not know what I is ahead of time? Yeah, you can just take the value 1 and left shift it I, and that's going to put a 1 at position I and zeros everywhere else. Does that make sense? Yeah.
Could you explain how to access this string?
Yeah. Well, again, like if you had a string, like a regular string, and you wanted to go through each of the characters in the string, how would you do it? You'd do loop, right? You'd access array at I, right? But here, you want to access bit I, and we'll talk about how we can look at what bit I is in just 1 second, right? But it's going to be using something like this, because this is going to allow you to put the 1 in the spot that you're interested in, right? And zeros everywhere else. So what would I do if I wanted to change bit I into a 1, right? I have num over here, and I want to change bit I of A to 1. What would I write here? So take 2 things. What operator do we use to change things to 1? OR, right? So we know that we're going to have to OR something, right? But we actually want A to change, so can I just write OR? Will that change A? We're going to have to do OR equals, right? Or A equals A or something, right? If you don't assign to it, it won't be modified. Now, how can I make it so that it changes bit I to a 1? That's just going to change bit 0 to a 1. I want to change bit I. So if I want to change a bit to a 1, should I put a 1 at that position or a 0 at that position? Come back up here. If I want to change, right, we know we're using OR. I want to change a bit to 1. Should I put a 1 at that position or a 0 at that position? a 1, right? Because if you OR something with 0, you're going to get itself. So this is always going to change bit 0, but I want to change bit I. So I need to get a 1 at position I. So how can I get a 1 at position I? We left shift it by I, because if we take 1 and we shift it to the left by I, a 1 ends up at position I, and you end up with zeros everywhere else. So this would let you change bit I of A to 1. Do you guys need to see, anybody want to see an example of how that's actually working? Sure. So let's put in a table here, or maybe we'll steal one of these ones. So what do you want your I to be? Oops. Right, this is the values of the bits that we have here, just represented as letters. Which bit do you want to change? Pick an I between 0 and 7. 3, right? So let's say we want to change bit 3. Right? So this is our variable right here, right? It's bits going across. Now when we just start with 1, well, 1 is the bit pattern 0, 0, 0, 0, 0, 0, 0, 1, right? Well, now let's take 1, and we wanted to shift it to the left by I, and I in this case is 3. So take 1 and shift it to the left by 3, and we move this 1 over, 1, 2, 3, and we bring in zeros to fill it in, and we have 1s everywhere else. Now when I do this OR with 1 shifted to the left by 3, right? Focus on this row right here. A OR 0 is A. B OR 0 is C OR 0 is C. D OR 0, again, focus on this row right here. D OR 0 is D. 1 OR E is 1, right? 0 OR F is F. 0 OR G is G. 0 OR H is H. And notice, we've now changed bit 3 to a 1. And, assuming that we actually did the assignment here, it says set var equal to what this value is. Var will change to be A, B, C, D, 1, F, G, H. Any questions here? Just been getting lots of questions about this, so I want to make sure we're clear on this. Okay, so what would you write to change bit I of var to 0? Which operator are we going to use? The AND, right? And since we want to change var, it's going to have to be AND equals, right? Now, if we want to change something to a 0, do we want to put a 0 there or a 1 there? 0 there, right? And we need 1s everywhere else, because A and 1 is A, but 0 and A is 0. It's going to force it to be 0 if we put a 0 at that spot. So how can I get a 0 at position I? So we could try doing, let's say, 0 shifted to the left by I. Now, if we try doing this, right, so here's var. This is 0. And again, let's say we're still trying to now change. Come on, get this line. change bit 3 to a 0. Well, this is 0. 0 shifted to the left by 3 is 0. And so var and equals with 0 shifted to the left by 3 is going to be 0 or a is 0. 0 or b is 0. 0 or c is 0. 0 or, not 0 or d. 0 and d is 0. 0 and e is 0. 0 and f is 0. 0 and g is 0. H and 0 is 0. So this would change everything in here to just be all zeros if we try to do this, right? Because 0 shifted to the left any amounts is going to be 0. It won't change, right? Let's say, though, we had tried to do it with a 1, right? So again, here's 1, and now here's 1 over here, right? But now when we AND it, right, we end up keeping the E and everything else becomes 0, right? Is that what we want? Was that our goal? No, right? But is it somehow related to what our goal was? It's the opposite of what we want. So how can I get the opposite bit pattern of what I have? Yeah, you negate it. So tilde, 1 shifted to the left by I. So if we take, that's 1 shifted to the left by I, and if we insert a row below, if we do tilde, 1 shifted to the left by 3, well, it's the opposite of the row above. So 1, 1, 1, 1, 1, 1, 0, 1, 1, 1, 1, 1. And now if I AND these guys together, if I AND these together, right, 1, if you just focus on the bottom here, 1 and A is A. 1 and B is B. 1 and C is C. 1 and D is D. 0 and E is 0. And then we're going to get F and 1 is 1. 1 and G is G. 1 and H is H. So A, B, C, D, 0, F, G, H. Right? And that will change bit 3. So all we need to do is stick a tilde on our 1 shifted to the left by I and AND it, and that will let us change bit I to a 0. Any questions? Now, what do you think flipping bit I is going to be? Right? What operator would we use to flip the bit? We just mentioned it a little bit ago. Which operator do we use to flip bits? It's the XOR, right? If we come back to the chart that we started with at the beginning, notice that if I XOR something, I can make it be the opposite of what it was, right? And again, it's only if I XOR it with 1, it'll become the opposite of what it was. If I XOR it with 0, it'll stay as being what it was. So here, if I wanted to flip bit I of var, well, I know I need to change var, so it's going to be an XOR equals. And so what do I want to put at position I? Do I want a 1 there or a 0 there? If I'd like to change the bit, if I want to change bit I, do I need to put a 1 there or a 0 there? A 1 there, right? So how can I get a 1 at position I? Just 1 shifted to the left by I, right? Like, notice the pattern has almost been universal every single time, right? We just change the operator, right? And then for AND, we had to negate the pattern. But each one of them was always variable, AND equals, XOR equals, or equals, 1 shifted to the left by I, and then in the case of changing it to 0, it was the opposite of that. The same pattern, rinse and repeat every single time, just combining these two things together, getting a bit at some position, use left shift for that, and then using the appropriate operator to modify. Do you guys have any questions here about changing bits? So one of the things you're probably interested in doing is looking at bits, figuring out if that bit's value is a 1 or a 0. Now, in programming, what's considered to be true and what's considered to be false? 0 is false, right? What's true? Everything else is true, right? Everything else is going to be true, right? So what we need to do is we need to get some expression that's going to leave us with either true or false, right? 0 or non-zero, based on whether we have a 1 or a 0 at that position, right? So you want to check if bit I is a 0 or 1. Now, which of these operators seems like it's going to be the most useful? And, or, not, or XOR, right? And a good way of thinking about this is, let's see an example. So let's say we wanted to check bit 3, right? And what we should focus on is our end goal. So we'll get rid of that for right now. At our end goal, if we wanted to check to see if bit 3 was a 0 or a 1, what would we want down here at the end to be able to identify whether bit 3 was a 0 or a 1? What would you want this expression to be here at the end? Discuss with your partner. Take a minute. Think about what would you like here at the end to be able to figure out if you have a 1 or a 0 at position 3, right? We want to check bit 3 is a 0 or a 1. Okay, so let's get back together. Let's break this down into two parts, right? Well, if bit 3 was a 0, what would you like this final result to be? Yeah, we'd like it to be all zeros, right? Because if bit 3 was a 0, you'd like to know false. That's identifiable, right? It was not set. Now, if you had a 1 at bit 3, what would you like your bit pattern to look like? Right? Because right now, right, if our bit pattern is all zeros, right, that's false, right? And it means the bit was not set to a 1, right? So if we want to be able to use some other value to represent it being set, we probably need it to be true, right? So we need this pattern down at the bottom to be what? What's our definition of true? Not 0, right? So we need a non-zero bit pattern down here at the end if we want it to be able to be true. And we'll say true means we have a 1. So what a decent bit pattern here be to be able to let us know that, yeah, E was, E, the bit at position 3 was 1. Yeah, it'd be fantastic if we could get a 1 to show up here, right? But at the end of the day, right, whether we get a 0 or a 1 here depends on what? What the value of the bit is at position 3. And so right now, what would be ideal to get would be E, right? Because if E is 0, this bit pattern will be 0, false, and we'll know that it's E was 0, right? The bit at position 3 was 0. If E is 1, this value, this bit string will be non-zero because E is 1. And so we're going to know that what we have right here at position 3 was a 1. So what could I do to make this bit pattern come about? What operator seems like it's going to be useful? AND, or XOR? Who votes for OR? Who votes for AND? Who votes for XOR? Yeah, I'm totally going to go with AND too. Right? I just need to hear you guys say it. So we're going to want to take var, and we're going to want to AND it, right? And what would our bit pattern over here, we'd want to AND it with be? What would you want at this spot? 0, right? 0, 0, 0, 1, 0, 0, 0. Right? This is the bit pattern that we'd like to get. How can we take our 1 and make it be equal to this bit pattern? Right? Because here we have 1. So what do we have to do? We have to take 1 and we have to move it to the left by 3, right? Which was our I in this case, right? Then you said we'd like to AND them together. So var ANDed with 1 shifted to the left by 3 will give us this result where we have 0, 0, 0, 0, E 0, 0, 0, right? This will allow us to check to see if the bit is 1 or not. Do we want to change var here? No, we don't, right? We just want to check it. So there's not going to be AND equals. It's just going to be AND because we just want to produce this new pattern without changing the original. So here, let's say we want to check if bit I is a 1 or a 0. What would you do? What do we do? Yeah. By. Yeah, right. And if this condition is true, what's that mean? If that condition above evaluates to true, what does it mean about bit I? Yeah. Yeah, bit I is a 1. Otherwise, that must mean bit I is a 0. Right? This allows you to check to see whether bit I is a 1 or a 0. What's wrong with this? Equals equals 1 or, equals equals true. What's wrong with doing this equals equals 1 here? I'll put parentheses here just so that we don't get confused. What's wrong with that statement? Yeah. It could be something not 0, but it doesn't have to exactly be 1, right? 5, is that 0? No, but it's true, but it's not 1, right? Even if you think about this pattern down here, this value, if E was a 1, would be 1, 0, 0, 0. What's that value there in terms interpreted as an unsigned number? Yeah, it's 2 to the 3, right? Which is 8, right? So is 8 equal to 1? No, but is this bit set? Yes, so don't set it equals to 1. It's not what you want to do. One other thing that I wanted to point out that I've seen is if somebody does this, what are they doing? Oh, this is not, oops, I forgot a word here. Pow does 2 to the I. I mean, some of you have done this in your code, right? Or something similar. It's not just one person I've seen do this, it's multiple. So someone here must know what they're doing. Yeah, you're trying to check to see if the ith bit is 1, right? But is that obvious? As obvious as this? I wouldn't think so, right? This looks like you're doing exponentiation for some reason, then ANDing the result, right? And yeah, you really will be checking bit I if it's a 1 or a 0, just like you were above. But this is also much more expensive to compute versus just doing the shifting to the left, right? This is because if we think about something in base 10, right? If I have like 1, 2, 3, 4, and I multiply this by 1,000, what do? You just add 3 zeros, right? You would just get 1, 2, 3, 4, right? You don't even have to think about it. It's just like add 3 zeros, and we're done, right? But if we couldn't, move 1, 2, if 1, 2, 3, 4, we couldn't add the zeros at the end, right? If we notice, if we shift this guy down a little bit, what does this look like we're doing with 1, 2, 3, 4? We multiply it by 1,000. What's it look like we're doing to 1, 2, 3, 4? Looks like we're left shifting it, right? We're moving all the bits to the left by 0, right? Because when you multiply by when you multiply the base to some power, right, you just add that many zeros. So if you multiply by 10 to the n, you just add n zeros, right? Which could also be interpreted as shifting something to the left by 10. Again, assuming we're working in base 10. But in the computer, we work in base 2. So if you do something like a times 2 to the n, right? A times pow to n. This is just a shifted to the left by n, assuming that a is an integer value, right? Does not hold for floating point representations because they're weird, right? But it's equivalent to shifting it to the left by n. Whereas if you multiply something by the negative n, well, that's equivalent, again, all integers here, that's equivalent to shifting it to the right by n, right? And finally, if you do this, a mod pow 2 to the n, well, this is equivalent to a ANDed with pow 2 n minus 1. And this whole and goes here. So if you mod something by 2 to the n, it's equivalent to ANDing it by 2 to the n minus 1. A good way of thinking about this is, let's say you mod something by 8. What are the possible values you could get? 0 through 7, right? Now, what's 1 or 8 minus 1? 7, right? So 8 minus 1 is 7. What's 7 in binary? 0b, right? 111, right? 3 ones at the end. Now, if you think about it, if you only have 3 bits, what possible integer or unsigned integer values could you represent? If you have 3 bits, right, you can represent 2 to the b things. So 0, 1, 2, 3, 4, 5, 6, 7. Oh, that's 8, right? So if you mod something by, or if you end it by 7, you're only going to be able to have values between 0 and 7, which when you mod it by 8, you end up with values between 0 and 7. Again, the same pattern would go up if you go up to higher powers of 2. So if you mod something by 16, you can get values between 0 and 15, which you need 4 bits for those values, the lower foremost. Or if you go up to 32, right, mod by 32, 31 is 5, or 31 will give you 5 ones, so you should be cool there, right? So those are some interesting kind of side notes about exponentiation in powers of 2, some base. But again, if your intent is to manipulate the bits, which is clearer, the shifting or the exponentiation? If all you're intending to do is actually move the bits, the shifting, right? Now, if you actually needed to do the exponentiation and you knew it was always going to be powers of 2 and you're working with integer numbers, you could, as like, an execution speed up, do a left or a right shift instead, right? Depending on whether you're multiplying by positive or negative powers of 2. But in general, I would say if you're doing exponentiation, it's probably just clear to do the exponentiation because that was your intent, and it carries much better through in your code. I've also seen some things like this. Come on. What's hard about reading this in terms of you as a reader? What's hard here? There is a lot of ones here. Do you really want to be counting the number of ones here? No, right? Because like if I was doing this, I'd probably be like, okay, space, that's 4. Oh, that's 4. That's 4. That's 4. That's 4. That's 4. 4. 4. 4. 4. 4. 4. 4 and 1. Right? But you can't write that in the C code, it won't work. But how many groups of 4 do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 groups of 1s, right? Assuming I didn't mess up in my counting, right? Now, each hex digit is worth how many bits? Not 8. A hex digit can have a value between 0 and what? 15. So how many bits would you need to represent the values between 0 and 15? 4. So every hex digit's worth 4 bits, right? Now, which hex digit has the pattern 1111? It's F, right? So if we were doing this, and again, this is maybe not the best example, but var OX, right? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Again, I would still say hard to read, right? But it's a lot easier to read. We also have this leftover 1 here. What's the representation of 1? 1, right? So 1, F, 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 which I'm going to argue is probably easier than reading, we had 4 times 14 plus 1 ones, right? Whatever that happens to be. 56, 57 ones, right? It's much easier. Or again, like, let's say we wanted to have something like 20 ones. What's 20 ones look like if you write it as hex? What's 20 ones? So every F is worth how many ones? Every F is worth 4 ones. So if you wanted 20 ones, how many S would you put down? 1, 2, 3, 4, 5. Okay, that's a lot easier than reading 20 ones, right? And so one of the advantages of using hex is that it gives us a very nice shorthand notation for writing very long binary strings, right? They're going to be a quarter of the length. So if you're working with long binary strings, don't do 0b. It's really hard to read, right? Just use the hex notation instead. Yeah.
So we are writing like 0xFFF. So what is the type of unit type?
What's the type of the literal OXFFF?
Oh yeah.
It's probably either like an integer or unsigned integer, but I'm not 100% sure. Like if you really want to get like specific with the types, there are prefixes you can add in the end, like U. So it's an unsigned int now. Or you can be like, unsigned long, unsigned long long. And so if you look at the documentation for C, you can see like what the prefixes are for the literal notations to make sure that you get the right type.
So could you explain what is the difference between signed and unsigned?
Oh, so the difference between signed and unsigned is unsigned numbers can't have negative values, but signed numbers can represent negative values, right? Which is a good follow-up. Let's say we have B bits. What's the range of numbers I could represent as an unsigned number? So if we had an unsigned number, what are the values that I could represent? Our lowest value would be 0. And what would our highest value be? So I'm hearing a lot of 2 to the b's. That's almost right. If we have b bits, how many patterns can we represent? If we have b bits, just in general, how many unique things can we represent with b bits? 2 to the b, right? Notice if you said your maximum value was 2 to the b, that's already 2 to the b plus 1 more for having the 0. So we could go between 0 to 2 to the b minus 1. Does this work if I do control? Nope. Control Shift plus? Okay, I don't remember what the format thing is to make it go. Superscript, Control plus dot. So that's 2 to the b minus 1 would be the maximum value that you could represent. What about for sign magnitude? So to help you kind of figure this out, let's say we had 3 bits, right? Bits XXX, right? This part right here is the magnitude, right? So we have 2 bits. So with 2 bits, what values could I represent if I only had 2 bits? Right? If we have 2 bits, we can represent 4 values. We start counting from 0. So we'd have 0, 1, 2, 3, right? We would have positive, up to positive 0 or positive 3, down to negative 3 if we had a 1 there, right? So notice we're using half of our bits to represent, half the bits, or we lose half the values because one of our bits is the sign bit, right? We lose 1 bit for representing sign. So that's going to take our values to be between negative 2 to the b minus 1 to 2 to the b minus 1. Again, if you think back to our example with 3 bits, right? Only these 2 bits give you magnitudes. 0, 1, 2, 3, right? That's the max I get with 2 bits. And then I have positive 0, positive 1, positive 2, positive 3, negative 1, negative 2, negative 3. So negative 2 to the b minus 1 to 2 to the b minus 1. For 2's complement, what would our range of values be? So, I messed up. It should be 2 to the b minus 1 there at the top, because half the values are positive, half the values are negative, right? For 2's complement, it ends up being negative 2 to the b to positive 2 to the b minus 1. So negative 2 to the b minus 1 to positive 2 to the b minus 1 minus 1. This is because the 0 representation gets lumped in with the positive numbers. That's why there's 1 fewer positive numbers. Does that make sense? And we'll do one other thing where you can mess with your friends if you want to, that know C. So let's say we have our int x, it's equal to negative 1. What's the representation for negative 1 in binary? Two's complement. Right, so you can imagine like you're at 0. If you're at 0, right, on our odometer, you wind it back. You end up back when you end up at 9999999. What's the equivalent of 99999 in 2's complement or in binary? It's all ones. 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1. Now, let's say we now have an unsigned int y and set it equal to negative 1. Yes, this is fine, But the pattern that ends up in here is just going to be 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. And when we interpret that as an unsigned number, what's 1, 1, 1, 1, 1, 1, 1? It's huge, right? It's the largest possible unsigned number you can get. Now, let's say we did this. If x shifted to the right by 1 is equal to y shifted to the right by 1, right? Print yes. Else, print no. So how many think yes will be printed? How many think no will be printed? Talk to your friends. See what they think. See if you can come up with a reason. So what are your guys' thoughts? How many of you guys are in the group that yes will be printed? How many are in the camp that no will be printed? For those of you that say no, why not? I mean, sure, if this was a test, you could just circle one, and I don't know why you think it's one or the other, but yeah.
So y is unsigned, right?
Uh-huh.
After you shifting y, is it still unsigned or it become a signed?
Y will still be unsigned and X will still be signed after the shift. The other thing is to think about is what does the computer use to represent everything? Everything in the computer is represented with what? What does the computer use to represent everything? 0 and 1, it uses bits, right? Everything in the computer is represented with bits, right? So when the computer is doing this equality test, what's it checking to see? Again, you're the computer, right? Everything you see is ones and zeros, right? Two things would be the same when what? If their bit representation is the same, right? If you have the same bit pattern, it's the same. That's why you can say, like, does A equal 64? Like, letter A equals 64? And the computer will be like, yeah, they have the same bit representation, right? Totally the same thing. There's no difference, right? So we know that X and Y, right, they start out having the exact same bit pattern, right? We then shift both of them to the right by 1. After you shift X to the right by 1, what are you going to end up with? So is it going to be this? Okay. If we take Y and we shift it to the right by 1, what are we going to end up with? In binary. Again, I'm not writing all the ones. There's a lot of ones. But just, you're saying, I'm assuming it's all ones all the way down. If we shift Y to the right by 1, what we get? So again, x and y, they both start with the same bit pattern. 0, 1, 1, 1, 1, 1, 1, 1, 1. So you said when you take x and we shift it to the right by 1, we end up with 1, 1, 1, 1, 1, 1, 1, 1. We take y and we shift it to the right by 1, we're going to end up with how many things? We're going to get lots of 1s. Same thing. Does anybody have any different thoughts about what you might get? Yeah. You bring in a leading 0? So you're saying when you right shift, you bring in zeros? So how many types of right shifts are there? 2. What are the 2 types of right shift? Arithmetic and logical. What does logical right shift bring in? Brings in zeros, always. And arithmetic brings in the most significant bit, right? So now the question here is, because there's 2 types, and for left shifts, right, how many left shifts are there? 1, and you always bring in zeros. So now we have to figure out, these right shifts, are they doing arithmetic right shifts, or are they doing logical right shifts? Because if they end up both doing the same shift, right, the answers have to be the same because they started with the exact same bit pattern. If they both do arithmetic right shifts, we're going to end up with 1, 1, 1, 1, 1. If they both do logical right shifts, we're going to end up with 0, 1, 1, 1, 1, 1. And the question is, do they do the same right shift? Yes, they both do the same right shift. No, they do different right shifts. Okay, for those of you that say different right shifts, what type of right shift will we do for x? For x, are we doing arithmetic? Or are we doing logical? So it seems like the consensus is arithmetic. For y, when we right shift it, are we doing logical? Or are we doing arithmetic? Seems like the consensus for those of you that voted was logical. And so it will be logical. So we end up with 0b. And the way that you can tell is based off the type of the variable. Signed numbers do arithmetic right shifts. Unsigned numbers do logical right shifts. So do those bit patterns match? No, so what are we going to print out? We'll print no, right? Because they're different. Now, if you really want to mess with your friends, now what will be printed out? Yes? No. Yeah, yes is going to be printed out because there's only one left shift, right? And you always bring in zeros, so they'll end up with the same bit pattern. Computer just checks the bit patterns, right? It's not smart enough to do anything else. And it will find that the bit patterns are the same, be like, yeah, they're the same thing, and it'll print out yes because you said to do that. Does this make sense? Any questions?
If it's unsigned integer, the bit pattern is choose complement.
If it's an unsigned integer, it's not using 2's complement. It's using unsigned representation, right? 2's complement is only if you want to represent signed numbers.
If it's unsigned, is what?
It just uses the unsigned binary integer representation. It doesn't use 2's complement because 2's complement is only for representing signed numbers, right? If you want a signed number system, you use 2's complement. If you want unsigned, you use the unsigned representation, right? This is why, if we interpret this 1, 1, 1, 1, 1 as an unsigned number, it's some massively large number, right? If we, though, if we interpret it as a signed number, it's -1, right? So again, it all comes down to interpretation. One interesting to note is no matter how much we shift x to the right by, its value doesn't change. Right? It's always going to be 1, 1, 1, 1, 1, 1, 1, no matter how much you move it to the right by. Now, one final thing I want to point out after we've done all that review is, again, everything in the computer, it really, really, really is only represented using bits and nothing else. And again, the bits only have meaning that you give to them. So what we might try is we're going to enter a value in hex here for this program. And then we're going to print it out in different ways. So we'll print it as a hex, as an unsigned number, as a 2's complement representation, as a floating point number, trying to interpret it, the first byte, as a character. Try to print it out as a string if it's possible. So we'll put in this bit pattern. So this bit pattern, again, I know you guys can work it out from the hex. But if we interpret it, again, hex is exactly what we entered in here. If it's an integer number, it's whatever that number is, 5,521,731, as both an unsigned number and as a 2's complement number, right? That's because your leading bits are, in our example, right, they're 0, right? And if it's 0, it's positive, right, for 2's complement, and all positive numbers have the same representation as their corresponding unsigned number. So that's why you see the same number printed out. It's also going to be interpreted as floating point 0, because it just so happens that your exponent bits are 0 with this number. If we interpret the least significant byte, it's the character C, and if we interpret it as a string, it's cat. Now, the interesting thing here is, which of these is actually going to be the least significant byte? The 0, 0 or the 4, 3, given that my machine is an Intel machine. Yeah, 4, 3 is the least significant byte, right? It doesn't really matter because that's what the number is. If we stored it, though, in memory, how would this integer be stored in memory? Given that my machine is little endian. Would it be... right? So it's going to be reverse order, right? Because it's little endian. So you'd see 4, 3, 4, 1, 5, 4, 0, 0, with 0, 0 being the null character, right? Stored in reverse order because Intel is little endian. If it was big endian, in memory, it'd be stored as 0, 0, 5, 4, 4, 1, 4, 3. So there's all different types of representations that you can give and meanings to these bits, right? This bit pattern, let's say we have something like A, B, 1, 2, 3, 4, D, D. This guy over here, right, he's some very, very large number as an unsigned number, some big negative number. Apparently, I still haven't had all of my bits, for whatever reason, for the exponent. I'll still happen to be 0 for the representation I picked. The least significant byte is some character we can't display, and we can't interpret it as a string because it's not null terminated, right? So there's lots of different possibilities for how these things can be represented, right, and interpreted. But again, it's all bits. I really want to drive that point home. So again, if you're ever asking, what's the binary? How do I get the binary representation of something? It's not a good question to ask because everything in the computer is already bits, right? It doesn't have anything else. The computer can just display those bits to you in a different way, right? In terms of like how it turns the pixels on the screen to resemble things that look like letters to us. Any questions? Yeah.
So if I have an integer and I want to print it in the binary form, so what can I do to this?
So if you have the integer and you want to see what its binary looks like,
Yeah.
well, if you see the first bit is a 1, what should you print? 1, right? If it's 0, you should print 0. If the next bit is a 1, you should print 1. If the next bit happened to be a 0, you should print 0, right? So you need to go through each of the bits, figuring out if they're a 1 or a 0. And then if it's a 1, print 1. If it's a 0, print 0.
So just use the bitwise operator.
Yeah, you have to use the bitwise operators to look at each specific bit, and depending on which, whether you find a 1 or a 0 there, you literally print 1 or 0 to the screen. Anything else? Okay, so that's chapter 1. We hope to have your quiz out tonight for you to get started working on that. And let's move into Chapter 2. So if you haven't been reading Chapter 2, get on that. If you have been, good. It shouldn't take us more than this week to finish Chapter 2. It's much, much, much shorter than Chapter 1. So inside your computer, there are two major parts. There's the hardware and there's the low-level software. The hardware are the things that actually execute the computer's commands or actually do the job. So like your CPU, it actually carries out the instructions. There's the memory, it stores values. There's your hard drive, which is your permanent storage for storing stuff after your computer gets turned off, right? There's your Ethernet card for connecting to the internet, or your Wi-Fi card for connecting to the Wi-Fi. You have your monitor, you have your keyboard, you have, all the physical things that make up your computer. We also have the low-level software that makes your computer run, which are going to be things like the operating system. It's doing things like managing the file system for you. It's making sure that processes get turns. It's making sure that processes get loaded into memory to be able to run. And they're also going to execute various system calls on behalf of your program. So when you actually say, hey, I'd like to print to the screen, what actually happens is you say, hey, operating system, I'd like to print to the screen. Can you do that for me? And the operating system is like, sure, I can do that for you, and it prints to the screen on your behalf so that you don't accidentally screw up the hardware that's there and mess things up. These divisions also lead to some portability issues. So hardware issues, programs compiled for one CPU will not run on another. So like a program's written for a MIPS CPU will not run on an Intel CPU. Or programs written for like a 64-bit Intel CPU won't run on a 32-bit Intel CPU because they have different hardware systems. Programs, though, written for older versions of Intel will run on newer versions because Intel is designed to be upwards compatible. So your old 32-bit programs will still run on your 64-bit programs. The other issue tends to be software. So since your program is going to be making operating system calls, those calls are handled by the operating system, and so we need to do something a little bit different depending on what machine we're running on. For example, scanf will make a call to read on Linux systems. So scanf internally will do that. But if you have scanf and you're trying to run scanf on a Windows machine, it's going to do Windows read, or whatever its equivalent is, right, to actually read those characters from the user's input. But the way that we invoke that read method is going to be different. They're not like the same operating system call, and the operating system calls aren't invoked the same way in Windows as they are in Linux. So if you put the Linux operating system call to do a read, and you try to run that on a Windows machine, it's probably going to crash the computer because either the system call will go through, but it does the wrong one, or system calls are invoked in completely different ways on Windows machines, and some other terrible thing happens, and it just breaks down, right? You probably noticed these divisions whenever you download a program off the internet. When you download programs off the internet, what do you notice about how they're versioned? Like, what choices do they give you? Right? They generally offer like, hey, do you want the 32-bit version or the 64-bit version, right? That's a hardware issue, right? The reason you only see like 32-bit version and 64-bit version and not MIPS version and ARM version and Intel version and, so all these other types of versions of different hardware like CPU sets is because like Intel and Intel clones dominate the market. So like AMD, their machines, they just are clones in some ways of the Intel architecture. So they obey all the same instructions. So since there really is like only like one chipset, like one CPU out in the world that everybody's using, that's why you only see difference between like 32-bit or 64-bit, or if you go way back in the past, like 16-bit versions. What other distinctions do you see when you go to download programs off the internet? Yeah, do you want the Windows version, or do you want the Mac version, or do you want the Linux version, right? And the reason you have to get all of these different versions is because they won't run on your computer otherwise for these stated portability issues, right? Because they're giving you the pre-compiled binary that should run on your own machine. If they were nice enough to give you the source code, right, you could just run your own compiler and turn it into an executable that would work for your own machine. But as you guys probably know, running the compiler is hard work, and it's easy to make mistakes, and your common user is not so savvy. So that's why they released the pre-compiled binaries. and also to protect their intellectual rights, because they don't want to like let you know what it is they're actually doing, because if you had their source code, right, you could just copy it and paste it somewhere else in the world and sell it as your version. And they want to make the money, not you. Any questions so far? So we're going to go through a high-level overview of the hardware components now. So the first is the CPU. A lot of times this is referred to as the brains of the computer, because it actually is going to execute the instructions of the program. It's the part that's doing the adding, the subtracting, the multiplying, telling the other parts of the computer that it wants to move values from this location in memory to some other location in memory. So it really is like the physical brain of the computer in that it thinks the thoughts, right? The thoughts, though, themselves are your program, right? So it's the one that actually carries them out and makes sure that it happens. There's the memory, which is going to store your program's instructions and data while it's running. There are various I/O devices, your input and output devices. These are what allow the computer to interact with the outside world. They generally display information to the user, and they, in terms of output, and then they have some form of getting input to the user. When you work with like a standard kind of computer, like what are your I/O devices? Now you have like your mouse, your keyboard, the monitor, speakers, right? You might also have like the Ethernet card might be considered to be an I/O device, or the Wi-Fi card to be able to connect to other devices, right? But there are also like other non-traditional devices that still have like I/O devices. Like for example, like the bank reader, right? You go to the ATM, right? There's the part where it like drags in your credit card. There's a part that reads the credit card, right? You have a little like touchscreen display for you to interact with. If you had some robot, right, there might be a camera for it to be able to see. It might have radar, right? It might have like motion sensors on it. It might have like, I don't know what you want to call like tactile sensors to feel like when it's run into something, right? That would be like how it's getting its I/O, right? Getting information from the user, and then it has some way of like interacting with the world as well, like with the robot arm to like grab things, right? Or like the wheels to drive it around. And then there's a system bus, and the system bus is just a bunch of wires that connects everything together, right? So that you can get information from your I/O devices into the CPU, or from the CPU into memory, or from memory to the I/O devices. It just allows stuff to be moved around inside the computer. So memory, there tend to be a few different types. The first is RAM, which stands for Random Access Memory. The random doesn't mean the memory is random. It just means that it takes about the same amount of time to access a random location in memory, right? So if you access location 0, you access the end, you access somewhere in between, it's going to take roughly the same time, right? This would be something contrary to like a video cassette tape, right, where it's not a random amount of time to access any individual scene on the video cassette, right? If your favorite scene is in the middle of the tape, right, you have to like fast forward through all the other stuff that's there until you finally get to the scene that you want to watch. If any of you guys have ever actually, if you guys still used VHSs, okay, I grew up with that. But at least you know they exist, right? And you have to rewind them and fast forward them. So, there was no like scene select on the DVD menu, right? It just brings you straight there, right? If your favorite scene was in the middle, you had to like fast forward and then wait until it finally got to that spot, and then you could like start playing and then go ahead and watch what was going on. So that's something of a non-random access device. It's also volatile. So when you turn off the power to your machine, you lose what's in RAM, right? It goes away. If you think about it, what's the most common like computer like diagnostic fix that you always receive from everybody whenever you contact them for help? What do they always tell you to do? Turn it off and turn it back on. And so the reason they tell you to do this is because what's in RAM, right, is going to get cleared when you turn it off and then turn it back on. And so what they're hoping is when you turn it off and you turn it back on and it restarts, is that you don't end up getting back into that weird state where things broke. Because, the states that are at the beginning of the, the device's running execution, they're probably very well tested, right? Because you had to go through them every single time the thing booted up. So they probably got most of the bugs out of the beginning. But the random kind of weird things in the middle, maybe those didn't get tested so well and they didn't get all the bugs out, and that's why you encountered your error. So the hope is that when you turn it off and you turn it back on, you start in a very well-known state where everything we've already got bug-free and it's working, and then you never end up doing that exact weird route that brought you to the bug again. And that's why turning it off and turning it on fixes things, right? This is also why when you're working like on Microsoft Word and you forget to save and all of a sudden the power goes off, you lose what you were writing. Because when you're actually writing and you haven't saved, all of the writes are going into memory, not onto the hard drive, because it's much faster to access memory than it is to access the hard drive. So when power goes out, since that stuff hasn't been written to the disk yet, what's in memory gets lost and you lose the progress that you had. There's also read-only memory. It's non-volatile. So when you turn it off, what's in here stays in here. This is where your system BIOS lives. And like the name read-only memory implies, you can basically only read from it. It's kind of a lie because probably some of you guys know you've had to update your BIOS before, right? You had to like flash your BIOS or have those be updated. So there are other types of ROM like EEPROM, which is electronically erasable programmable ROM. And what that means is when you put normal voltage through your ROM, you can only read through it and you can't change what's there. But when you set a very high voltage through the EEPROM, you can actually change its contents and set it to be something different. So most of the time it's read-only, and occasionally you can change it. That's why it's really important when you flash your BIOS that you don't accidentally lose power, because it's being updated then, and the BIOS is what actually kind of like starts your computer up and running. So if it gets screwed up in the middle of updating, it's probably going to brick your computer, and you won't be able to use it again, which is very sad. The final thing I should say here is that this is not your hard drive when we're referring to memory in this class. That's considered to be an I/O device, some other external thing where we can put information to. Any questions on memory or anything else? Yeah.
What's like the most secure form of memory, like that's access or?
So like, what do you mean by like secure? Like as in not hackable?
Like very non-volatile.
So for example, like what they use on the hard drive, right? That's where your like the entire contents of all of your system's files are stored at. Like so, everything that makes up your computer's data is actually placed on the hard drive, and then when it's needed, it's brought into the RAM, because the hard drive is very, very slow to access, but the RAM is a lot faster, so it'll just make a copy in RAM and to be able to work with it there quickly. And then when you no longer need it, it'll go put it back onto the hard drive to be able to free up the space for other things. Now, the way that like traditional hard drives work is they're magnets, right? If you've taken like Physics 9C, you probably maybe remember that like a moving electrical current produces a magnetic field, and a moving magnetic field produces electrical current. So what they do is they'll spin the magnets either like positive or negative in the hard drive, and so when they spin the platter, depending on its orientation, either positive or negative, it'll produce like a 1 or a 0, and that's what they read it back out. They also have like other things like flash memory, which is if you have like a solid state drive, that's what that's made out of. And I'm not quite sure how it's actually built because I didn't really study that. So there's the I/O devices. Again, they just allow you to interact with the computer. There's lots of different things out there in the world that allow you to do this. There's a system bus. It's like the roadway of the computer. It doesn't actually store anything, but it allows you to get data from one spot to the other. It's really just a bunch of wires. If we want to think about it, though, these sets of wires can be broken down into 3 sub-buses or to 3 subgroups. There's the control, the address, and the data bus. The control bus is used to send control signals like I would like to read or I would like to write. The address bus tells you where you like to read from or write to. I want to read from address 10. I want to write to address 10. The data bus is the value that you actually want to read or write. So if the control bus wants to do a read, right, then the data bus is going to contain the value that it read from memory or from some other I/O device after it's completed the request. If the control bus wants to do a write, then it's going to put whatever value you want to write. To say the CPU wants to do a write, it'll put set the control bus to be a write, it'll put the addresses to where it wants to write it to on the address bus, and then it'll put whatever data it wants to write into the data bus, and then that information will be moved to the correct location. So just a bunch of wires. It really is just a bunch of wires used to send information across the computer or inside the computer. So let's talk about the CPU. The CPU is probably one of the more complex pieces of your computer, and it can be broken down into a couple of different parts. The CPU has its own little internal bus to communicate with the various components that are inside of it. It has the ALU. The ALU stands for the Arithmetic and Logic Unit, and unsurprisingly, it does arithmetic and logic. So this guy right here, he's the part that's responsible for doing the addition, the subtraction, the multiplication, the division, the anding, the oring, checking if this value is 0, checking if this value is 9. It does those checks, but it doesn't actually store any values. Where the values are going to be stored are in what's called the CPU's data registers. In this case, they are things like EAX, EBX, ECX, and EDX. So when the ALU wants to do some operation, it's going to read those values from one of its data registers, A through D, compute whatever the result's supposed to be, and then store the result back into one of the registers. It could also, though, choose, because we're working with Intel, to read one of the values from memory or to write one of the values to memory. There's the program counter right here, which is also called the instruction pointer, and in Intel lingo, it's EIP for the extended instruction pointer. It holds the address of the instruction that you're executing, right? So if EIP had address 500 in it, we'd be doing the instruction that's at address 500 in memory. ESP is the stack pointer. So the stack pointer keeps track of where your program stack is at, the top of its stack. The memory address register, when the CPU wants to do a read or a write, it'll set the memory address register to be where it wants to read from or write to. And then the memory data register is, if it's doing a write, it'll put the value that it wants to write in here. If it's doing a read, the value that it ends up reading from memory will be placed here. And all of these registers that you see here, right, these guys are all registers. The ALU is not. It's just some combinational logic that does the arithmetic and logic. These guys are all going to be word size. So if we're doing it with a 32-bit Intel CPU, all of these guys would be 32 bits big. The only exception to this in terms of size is eFlags. This is your flags register, and the flag register just stores various random bits of information about what has happened or in like what the permissions are. And it's going to be as big as it needs to be able to fit everything. So there will be bits here to figure out, like, was the result of the last operation a 0? Was the result of the last operation, did it cause a carry or did it cause an overflow? Are we in user mode, or are we in like kernel mode? That type of information is kept inside the eFlags register. And finally, there's one other register that's not actually showed here. It's the instruction register, IR. And it stores the instruction that's being executed. And again, PC stores the address of the instruction being executed. The instruction register stores the instruction itself that's actually being executed. I think I talked about each of those things. And we have a little bit more that we'll talk about on Thursday about the Chapter 2, but we'll finish on Chapter 2, and then we'll be into Chapter 3, and we'll actually be talking about how to write assembly code. Woo!
I want to ask about how to use the get line stuff, like